Hi everyone, and welcome to our video titled Volume of Solids with No Revolution. That's the key difference here between what we've been working on over the last few days and what we're going to start today. We are not going to be spinning anything around an axis or a line to create volume. We're going to be going about it a slightly different way. So you see these notes start with these three pictures. I'm actually going to come back to these pictures in a moment. I actually want to go to the example, the first example first, and then we'll see how the examples and the answers tie into these pictures. Okay, so if you look at example 1, it says find the volume of the solid. So it's starting off with the same phrasing we've been using. But here's what's interesting. Whose base is bounded by the graphs of, and then they give us some graphs here. So they give us y equals 3, y equals 6, x equals -4, and x equals 4. So the one key ingredient is when you have no revolution, but you're finding volume, the problem will always give you information about the base of your object. For example, like this tape dispenser right here, I'm just grabbing things on my desk, this tape dispenser. If I turn it upside down, I see a rectangle, sort of, kind of. Actually, I see a trapezoid, check that out. If I take this dish of paper clips, if I turn it upside down, oh gosh, I don't think this is very smart, but let me try it. I see a circle. Okay, so they're giving me information about the base of my solid. So what I did here, and feel free after I show you this to pause the video if you need time to draw, I took a piece of graph paper and I drew what the base is bounded by. So what I did is I drew an x-axis and a y-axis, and I graphed the lines. Here's y equals 3, here's y equals 6, here's x equals -4, and here is x equals 4. So your base here is a rectangle. So when you pick up your object and turn it upside down, this is what you see, a rectangle. And there are tons of objects in the real world whose bases are rectangular. Now, let's keep reading the problem to see what they say next. Then they go on to say, so here's your base, and whose cross sections cut perpendicular to the x-axis are, and then they start in with different cross sections. So we're going to start with letter A. So when the cross sections are squares. Now here's what's interesting. Up until now, we have only been dealing with cross sections that are discs or washers. And the discs and the washers came about because of the revolvement, the spinning around the x or y axis. So those were sort of natural cross sections. Now we're sort of being told what our cross sections are. So can you envision, now this is where you got to have that kind of 3D brain that I've gotten better with over the years. Can you envision an object that when you turn it upside down, you see a rectangle? Now it's solid and growing up out of the base. So I'm talking about the cross sections cut perpendicular to the x-axis. So if I cut in,
Madison Braden, please report to the main office.
Sorry about that.
Madison Braden, please report to the main office.
So when I cut in to this already three-dimensional object and I look in this way, I see squares. So you have to envision that here's the base and something's growing up out of it. Okay? So what I snipped off the internet was this piece of chocolate. I thought this piece of chocolate right here kind of, or is it a brownie? I'm not sure, kind of mimics what this situation's asking for, because if you turn it upside down, you might see a rectangle as the base, but it's growing up out of it. If I were to cut into this piece of chocolate, slicing cross sections, they would be squares. See that square there? And back further, square, square, square. Okay? So we're going to find the volume of such an object. So what we have to think of is there's no revolution. So that's what's really cool. You don't have to worry about revolution. So you're really just going to, you ready for this? your volume is just simply going to be adding up, that's the summation, from, let's go back to our picture, from -4 to 4. Those will be my boundaries. So I'm adding up from -4 to 4. The area of a cross section. So let's think about if I were to cut into this piece of chocolate, right? If I were to cut into this right here, do you see how one of the side lengths of a cross section is actually the distance from here to here? Okay? And then the height, now you got to envision this is growing up out of the base. If the cross section is a square, then whatever length this is, this height of your cross section will be the same. So we know that length or distance right here is going to be the top minus the bottom. Because the top would give us all of this, the bottom would give us that, and so right here, bingo, that's what we want that's left over. So if I take 6 minus 3, I get 3. So what I'm going to write here is the area of a square is a side length times a side length, and then dx. This is area of a square, area, messed that up, area of one square cross section. So S times S is the area of one square cross section. We're going to add up the infinite amount of cross sections in the space to give us our final answer. Now the last step here is we have to get S in terms of X. Well, I think I just established that my side length is 6 minus 3, which is 3. So I'm really taking 3 times 3 dx, which is equal to the definite integral from -4 to 4 of 9 dx. And if I can either plug it in my calculator with Math 9, or I can run a quick fundamental theorem. This one's pretty easy. Why don't I do this one by hand? So this would be, antiderivative would be 9x, and I'm going from -4 to 4. And then if I plug in my upper bound, I have 9 times 4 minus 9 times -4. So that's going to be 36 plus 36, which is 72 units cubed as my volume. Okay, now here's what's interesting. We could check this with geometry. If you think about this piece of chocolate right here, let me bring this back down. Here's your piece of chocolate. So if this had been 3, right, and this had been 6, so we knew the base was 3 by 6, but the height is also 3 because we know our cross sections are squares. If you take, length times width times height, then the check here by geometry would be 3 times 3 times 6. What am I messing up on here? Wait a minute. What am I not taking into consideration? That's not 72. What am I messing up on here? Wait a minute. 3 times 3 times 6. Miss Bleacher, do you know what I'm messing up on here? Because this would be 3 by 6 by 3, right?
Yeah.
That's 54.
Yeah.
What the heck? Do, 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 do. Oh my gosh, it's not 3 by 6. Callahan. Hold up. Look at my picture. It's 3 by 8. Duh. Okay, so the base area it's really from -4 to 4, it's 8 by 3. So change it. See, teachers mess up too. This is 8, not 6. For some reason, I had that 6 in my brain because of this being at y equals 6. I have no idea. So 3 times 3 times 8 is 72. Okay, I was like, oh gosh, do I have to redo this video? No, we caught it. Okay, so there you go. You made it through your first volume with no revolution. Okay, let's go to the next one. Same problem, you guys, same base. But now, growing up out of the base, that's a rectangle, are semicircles. What the heck would that look like? Well, I got a picture here for you. Check out this. So you see the rectangle here? Let me highlight over it. It's actually kind of upside down. The base is actually facing upward, but here's your rectangle right here. I'll highlight on it. See, it's a half of a log. So here's your rectangle, but look at the cross sections. If you can see here, it's hard to go over this black, but your cross sections moving back through the space are semicircles. So again, think of this as being like the 8, and this is the 3. That's your base. But now we have to add up the infinite number of semicircular cross sections that are growing up out of the base. So really, all we have to do to set this up, again, is just, there's no revolution, so volume equals, we stick with -4 to 4, just moving through the space. But now, we don't need the area of one square cross section, S times S. We need the area of one semicircular cross section. So like whatever your cross sections are, that is what you put, that's the formula you put right here inside your integral. Then you just get it in terms of x. So for a semicircle area, we need pi r squared, so that's your whole circle, but then we're going to have to divide by 2. So all we'll have to do to get this answer is find the radius of our semicircle in terms of x. Okay, so this is going to be the definite integral from -4 to +4. Pi, I'm going to leave room for r squared divided by 2 dx. So I just have to find that r. So let's go back to the picture. Now, if you look, here's my base again. That's the part of the tree there. That's the part of the log. We already know the diameter. Now imagine this is the diameter of a semicircle, and then watch my pen. Growing up out are the semicircles. So if the diameter is 3 units, then the radius is going to be half of 3, which is 1.5. So that's what I'm going to plug back into this formula for radius. So 1.5 squared divided by 2 dx. And again, we could square that out, divide by 2, and run the fundamental theorem. For time's sake, because this is a video and I'd like to try to keep it somewhat concise, I'll just go ahead and evaluate this on my TI so we can move it along. Get this out of the glare. Okay, so we've got Math 9, definite integral, -4 to 4. And then we've got, I'm going to create a fraction here. I need a pi and a 1.5 squared, and then all over 2. And this is with respect to x. So we're adding up the infinite number of cross sections, the areas of those, and I'm getting 28.274. So 28.274 units cubed. Final answer. Okay? Final problem here on this first example. Same base. We're still going with a rectangular base, but now our cross sections cut perpendicular to that base are equilateral triangles. Now, I don't know if you ever heard of this candy, but there's this candy, fancy candy, I think it's kind of expensive, called Toblerone. This really is real, okay? And there it is. That's what it looks like in the packaging. So look here, you have this rectangular base. If you would pick this up, turn it over, you're going to be looking at a rectangle, but growing up out of that rectangle are these equilateral triangles, and they move all the way back through the space. So you're going to add up the areas of the infinite number of equilateral triangles through the space. So again, my setup is quite easy to start. I'm just going to do volume equals the definite integral from -4 to 4. That makes sure I get all of them. And then I need the area of one equilateral triangle dx. Okay? Well, the area of any triangle is just 1/2 base times height, right? 1/2 base height. So I'll just have to get the base and the height in terms of x. So again, one more time, back to my picture. Here's what you got to do, and this is where in 2D this is so hard to envision, but like, okay, here's the bottom or the base of the equilateral triangle. That's 3. So this B right here is going to be a 3. Now, envision for me, again, watch my pen coming up out of the paper to the point. There's a side of the equilateral triangle, then dropping back down is the other side. So you've got your base, side, side. If you're looking at the picture here, you've got this base, which is the 3, and then you've got this side and this side that are growing up out of the base. So what I like to do with these is I like to take a part of I like to take a full cross section. So I'll come down here like this, and I'll draw, okay, there's my equilateral triangle, and I know the base is 3, and that's the top minus the bottom here. Well, if it's equilateral, then all of these are 3. And now what I need to do is find my height, because I already have my base. So my height, well, I could do Pythagorean theorem. That would be one way to do it, because if I cut a height here, it's going to split my 3 into 2 parts. So this is going to be 1.5, 3, and then I have a height. So I could run a quick Pythagorean theorem and say h squared plus 1.5 squared equals 3 squared. So h squared plus 1.5 squared is 2.25 equals 9. And then subtract. So 9 minus 2.25 is 6.75. And so the square root of 6.75 will give me h. Let's see how ugly that is. Square root 6.75. It's ugly, so I'm probably going to leave it under there. Okay, square root 6.75 is my height. So here we go back to the formula. So my final answer is going to come from the definite integral from -4 to 4 of 1/2, 3, which is my base of my cross section, and then my height of the square root of 6.75 dx. And again, for time's sake, I'm going to go ahead and pop that into my TI. So Math 9, I've got -4 to 4, 1/2 times 3 times the square root of 6.75 dx. And I'm getting 31.177. So final answer, 31.177 units cubed. Okay, so there you have it. Now, that's one example. Now, if you look at the back of your note sheet, there is another example, and I will make a video for this. It'll be the next video in the series, but I'm going to cut this video off here because it's already pretty lengthy, and we'll do the example 2 in the next video. Okay, thanks for watching.